So I took inspiration from an earlier talk today and added the word towards into the title. So I'll be talking about some work that we're doing towards using probabilistic programming for more reliable machine perception. And that's things like 3D computer vision and robotics. And this is about reliability at a different level than the earlier talks. So instead of talking about how do we make sure our implementations of algorithms are bug-free or accurate, this is saying what are the modeling approaches that we might want to use to make machine perception in general more reliable, and how can probabilistic programming help make those modeling approaches easier to use. So first I'll show a couple videos showing some sorts of machine perception algorithms and talking about what about their output doesn't match our human common sense understanding of what we think the right answer is. Oops. So here's a segmentation algorithm running on some data from a video of a street, and the truck in front of us, if you look at the bounding box around it, the confidence that the truck exists is sort of fluctuating 80 to 90%, dipping to 70%, going below the threshold for which the visualization is choosing to show it, right? So why is the probability of this truck's existence fluctuating so much? That doesn't really match our human common sense understanding. Here's another video. This is a really exciting piece of work out of NVIDIA last year, and this technique is inferring the three-dimensional pose, which is the position and orientation of objects in 3D space. So there's a couple, this is really impressive work. There's a couple things that don't make that much sense from a human perspective. One is, why are these results flickering so much, like we saw before? But also, sometimes you just get these wrong pose estimates. So for this mustard bottle, these two frames are just showing the incorrect estimate. And that's something that, that's a sort of error a human would probably not make. Okay, and then here is a sort of adversarial example of some issues. I don't know, how many of you have seen this video? Oh, cool, okay, so this is a 3D printed turtle, and it's classified correctly as a turtle from all these angles by one of Google's classifiers. The authors of this work in ICML printed an adversarially perturbed texture on top of the turtle, and they actually are able to make this turtle be classified as a rifle from every angle by this particular classifier. So, right. So, how can we use how can we use what we think of as common sense human reasoning and the ways that we think about these problems to maybe detect or prevent these sorts of errors? And I think a general principle that we're going to try to talk about in this talk is leveraging our prior knowledge, more of our knowledge about the world. So these sorts of flickering problems that we saw in the beginning, right? These are understandable because these are algorithms operating on individual frames. So there's no notion of temporal consistency. So maybe we can build on top of these systems some sort of notion of temporal consistency, and there's lots of tools for doing that from probabilistic modeling, like hidden Markov models. For these other sorts of errors where you just get inferences that are just plainly wrong to a human, how could we try to detect those? Well, we have some prior knowledge about how images are formed. So suppose we actually had a three-dimensional mesh model of that mustard bottle, and we had a texture for it. Then we could take any proposed pose that the algorithm gave us and render what the image should look like, or what that object should look like from that perspective. And, right, so in this case, we should expect to see something like this in that image area, and we should be able to define some sort of simple way of checking whether that image patch looks like this, and it clearly doesn't. So something might be going wrong here. So in this case, we'll be using our prior knowledge about 3D models of the object and our prior knowledge about how images are formed via a graphics simulation. And in principle, maybe we could apply the same problem to this sort of example over here. in order to do so, we might need, for example, a database of all possible models of rifles, 3D models of rifles, and we might need to consider searching through that database, is there any rifle model that exists and any three-dimensional pose of that rifle relative to the camera such that this image could be produced? And if we can't find one, right, then that means this is probably wrong. Okay, so there's other types of knowledge too that we should be able to leverage that humans may be using. So for example, in the pose estimation problem, these objects are not just sort of independently being generated at different poses in space, right? Objects have a physical relationship. They're resting on one another. So if we have some blocks, we can either model those blocks as sort of having independently sampled poses randomly in space, or we can model them through some sort of graph which actually describes their relationship, spatial relationships. And this should help us improve our pose estimation. And also maybe the physical relationships here may actually be of intrinsic interest to whatever we're trying to do with the scene. So again, in each of these cases, we think that if we leverage some more prior knowledge and combined it with these approaches, we could get more reliable inferences. Another aspect that we want to take seriously here is uncertainty in our inferences. So here's an example of a pose estimation problem where I have a coffee mug, let's say, and I have two images of that coffee mug. So on the left, top left, there's an image where I can't see the top or bottom of the mug. So I don't know whether it is upright or not. But I know basically the right angle because I know where the handle is. So these are two possible poses that are consistent with that image on the top. On the bottom, if I can't see the handle at all, then I have even more uncertainty. So now I have, again, it could be upright or down, and then actually there's a whole range of angles at which the handle could be. So this is an example of a multimodal posterior distribution where I have multiple distinct hypotheses for what the answer could be. And if we want machine perception systems that are more safe maybe and more reliable, having them be able to report when they don't know instead of arbitrarily giving one of these answers would be desirable. And there is some work in machine perception that is taking uncertainty seriously, but again, it's not exactly the mainstream thing right now in deep learning in particular. Most people are still talking about giving point estimates. And there's more exotic types of uncertainty too that a human might be able to express when they look at a scene. So if I see a scene here from the camera's perspective and I just see a red box, now I don't know whether there's this object behind the box or not. Well, if I'm told that there is an object behind the box, then I can propose all these possible locations for the object behind the box, so all these different poses, right? If I'm told that, well, the object is probably behind the box, but I'm not sure, then we can cast this as an inference problem and actually ask what is the probability the object is behind the box. And depending on the box's angle relative to the viewpoint, this probability is higher or lower. So this is an entire set of modeling approach where we want to combine both prior knowledge as well as accurate uncertainty quantification. And it seems like probabilistic programming could be a good fit for this because probabilistic programs, the probabilistic programming paradigm involves writing models which express your prior knowledge in modeling languages. And these languages are expressive enough to encode lots of the types of knowledge that I was describing. So knowledge about physics, right, the physical temporal consistency of a scene, or knowledge about how graphics works. And again, probabilistic programming languages typically are based in Bayesian inference as the goal, so they encourage a principled approach to uncertainty. And finally, right, they are partially automating the inference process, so they should be improving the productivity, improving the accessibility, and reducing the bugs that users might encounter. So there are challenges, though, in applying probabilistic programming languages in this sort of machine perception context. One big challenge is that most of these languages have been developed from a sort of statistics paradigm, and they haven't really been designed for sorts of applications like computer vision or robotics, where there's very different performance constraints. So for example, my inference needs to run in real time. Maybe I need to make trade-offs between the accuracy and its running time, or other constraints like memory usage, things like that. Whereas in other applications, maybe statistics, maybe it's okay just to run the MCMC algorithm overnight, and we get the results that we get, and it's the best we can do. So in this talk, I'll be talking, one of the things I'll mention in the first block of the talk is what we've been doing to create probabilistic programming systems that are more aligned with the needs of areas like machine perception. And a big piece of this is allowing users to have the ability to specialize the inference procedure to a high degree, and also incrementally optimize its performance in a very flexible way. So that's this GEN system, which was presented at PLDI this year. And then the second part of the talk is about how do we measure the error of some inference procedure. In particular, if we're in this performance-constrained domain where we actually are trading off error and running time or other resources, how do we make that trade-off in a rational way? So we need ways of measuring the error of our fast inference procedures. And to do that, I'll talk about some work on estimating these errors quantified using KL divergences, which we saw earlier today. And this was published in NeurIPS in 2017. Okay, so I'll try to get through most of this. I might skip some of the details on GEN system architecture. That's in the PLDI talk. But let's see how we go. So GEN is, again, designed for more inference specialization than existing systems. And so I'm going to basically plot GEN here on the axis, showing how it relates to other systems. So the two axes here are modeling language flexibility and inference flexibility. So some probabilistic programming languages are sort of in this lower left corner here. These are among the most popular and widely used and widely adopted systems, Bugs and Stan, and they have more restricted modeling languages. So for example, Stan requires models to be differentiable and requires them to have continuous variables only. And Bugs, for example, requires there to be a fixed number of random variables in your model. And those systems also provide pretty restricted inference functionality that's basically based on inference engines, right? So a fixed inference algorithm or a set of algorithms that they're providing. And that is actually a pretty workable part of this design space. Because the models are more restricted, you can have inference engines that work fairly reliably and solve most of the problems people write in them. So that's one reason why these have achieved pretty good adoption, I think. There's also been a set of probabilistic programming systems in this other corner where they've taken the modeling flexibility really high. So systems like Church and Eyeball are based on the idea that you can express models in general purpose programming languages with all the interesting features of those languages, like things like recursion. But these particular systems also try to provide relatively fixed inference engines. And it's interesting that actually you can write down asymptotically valid algorithms for any of these large class of models, but having those algorithms actually work efficiently in practice is a pretty tall task because of the expressiveness of those languages. So over time, a lot of work has been done moving to the right here, so trying to add more inference flexibility, allowing the user to customize the algorithm more. And this is the upper right corner of this area is we're calling programmable inference. This is a term that's introduced in this Venture PLDI paper in 2018. And in programmable inference, really, inference is actually not like picking an algorithm or picking an inference engine. You're actually writing some inference code, but you're writing it at a pretty high level of abstraction. So you still have to think about your inference algorithm design as a user. And GEN is situated definitely in this area over here, and it builds on some ideas in Venture, has some similarities to Pyro, and relative to Venture, it's significantly more practical for solving problems, and I'll show an example of that later. So now so I guess I'll show that now. So now I'll talk about a couple examples of how GEN has been applied. So one type of problem is can we infer the 3D pose, meaning the orientation of the joints of a human body model from some image of that person's body? So similar tasks have been addressed in other papers, going from images to underlying body poses. Here we're looking at a simplified version of this task where we go from a depth image, which is just, each pixel provides the depth relative to the camera, back to the underlying pose. And I'll go into some detailed Gen code later on in the talk, but I want to give a high-level overview of sort of what are the features of Gen that make it practical for this sort of application. And one feature is that Gen allows you to use custom proposal distributions parameterized by neural networks. So for this particular problem, we're using two systems, Gen and Turing, which is another system implemented in Julia, and Gen is also implemented in Julia. And we're showing that Gen outperforms this Turing implementation because it allows you to use a custom neural network instead of a generic proposal distribution. So that's one important dimension of flexibility. And the way that we implement this, well, first we express our prior knowledge in our probabilistic program, and our prior knowledge includes a distribution on poses of the person, the 3D mesh that we're using, as well as this image generation process that takes the mesh and goes to the image. So all of that is our prior knowledge we're bringing in. And the first thing we do is we train a neural network to propose the underlying joint angles from the image, and that's done offline. And after training, we get a proposal distribution which is sort of solving the problem, but it's not exactly doing what we want. So it has this residual uncertainty about the elbow angle for some reason. So at inference time, we take a new test image that we're given, and we are going to run our neural network on it, generate a bunch of proposals, and then we're going to filter out those proposals based on whether they match with our prior knowledge, or whether the reprojected image or the re-rendered image we would have gotten from each of the proposals matches our actual image. So this is an example of that principle I was talking about earlier, where we could render the mustard bottle from that orientation. And this is implementing, this algorithm happens to be importance sampling, so there's a Bayesian interpretation to this algorithm. But the intuition is that we're combining a neural net-based proposal with this check based on rendering. So this is an example of using deep learning to help Bayesian inference, making it more efficient by taking some of the cost and amortizing the training cost over many possible problem instances. And actually, as a side note, using stochastic simulators to generate training data for deep learning is very popular in deep learning. And there's a perspective here in which if people in deep learning, from that perspective, if they implemented their simulators in probabilistic programming languages, then they could actually also gain additional robustness. And the key idea there is that they're using their prior knowledge at inference time and not just at training time. So that's a high-level side point here about how probabilistic programming and deep learning might relate. Okay, so another problem that we've addressed in Gen and benchmarked is inferring the symbolic structure in a time series data. And this example illustrates the expressiveness of Gen's modeling language. So the thing we're inferring here is a symbolic expression in some simple expression language. And the expression basically talks about the types of structure in the data set. So there's some composition of periodic trend with a linear trend. And we have some DSL for expressing possible structures. And then we're inferring that expression from the data. And then given that we've inferred the structure, we can make forecasts that are actually pretty precise. And Gen is the only probabilistic programming system besides Venture that can actually implement this particular MCMC algorithm we're using for this problem, and as far as I know. And the implementation of Gen, which is based on pretty different architecture than Venture, gives 100x speed up. This is one of the key performance pieces of our PLDI paper benchmark. Okay, so that was a little taste of the sorts of things that you can apply Gen to. Now I'll go more carefully into a step-by-step example and show some code. So here is a video. On the left is a depth image from a real-sense depth camera, and on the right is showing a segmentation of that image into which pixels correspond to the floor, and those are the blue pixels, the floor of the ceiling, I mean. Red pixels basically mean missing data, so the sensor is just not giving us a value. And in the middle, I'm showing a virtual world, which is going to be our explanation of the data on the left. So our virtual world just actually has two things in it. It has floors and ceilings. So all we're modeling is the floor and the ceiling, and the relative pose of the camera relative to the floor and ceiling. And we're doing that over time. Now I'll go into some of the code that we can use to solve this problem. So in Gen, basically, every piece of a Gen program consists of two components. There's a generative model and an inference program. And the generative model basically is responsible for simulating virtual worlds and then generating virtual images from those worlds. And the inference program, broadly speaking, its job is to take a real image and go to virtual worlds that explain that image. So now I'll go into each of these pieces in turn. So for the generative model, you write, like we saw some earlier talks, probabilistic programming languages. This looks like a pretty similar syntax to what we saw earlier. So this is a generative function, or an @gen function, and it's kind of similar to Julia's syntax, if you're familiar with the Julia language. But basically what this does is it's generating a virtual world. Well, it says there's some floor in this world, and there's a camera, which is where our viewpoints are going to be taken from, and that camera has some unknown z coordinate, right? So we're going to sample that from a distribution between 0.2 meters and 2 meters. And we're going to give that random variable a name. This is similar to Pyro's naming scheme. We're going to call that z. And then we're going to sample a pitch angle for the camera from some distribution, and a roll angle as well. So those are the three random choices in our program. And then we're going to render the resulting image that we would have gotten from that camera. And we're going to be doing this just with depth images for now. So again, the image on the left is the sort of the synthetic depth image we might get if the camera was in this particular pose. And then we have some noise model we add on top. So the noisy version of the image is going to have name observation. Okay, so the inference program is actually just regular Julia code. There's no additional DSL introduced here. And what this program does is it first gets an image from the depth camera, shown in the upper right, and then it generates an initial execution trace of our generative model. So this notion of an execution trace is a common abstraction used in probabilistic programs, but it basically represents an assignment of all of the random variables to particular values. And the trace we get out initially samples all the random variables from the prior distribution, except it sort of takes the observation as a constraint and it fixes it. And when we do that, basically we get a trace which is a complete trace of our generative model, but it's a little bit incoherent because the random variables, like the angle of the camera, don't really match with the observations, right? So initially we're saying that the floor is at this angle, whereas the camera looks like it should be horizontal. So resolving that discrepancy is the role of the rest of this inference program, and basically we're going to apply MCMC in this for loop. Oops. And what this is going to be doing is starting with some random initialization and then gradually improving the virtual world. So at the end, we're going to return the final execution trace. So now each of these steps inside is applying some MCMC operator to the execution trace. And here we are basically asking Gen, this is Gen's MH operator, which stands for Metropolis Hastings. We're asking Gen to pick new values for the pitch, roll, and z coordinate variables. And here we are asking Gen to actually do a different type of update where it only incrementally makes small adjustments to individual variables. So basically this move here is going to be responsible for making big jumps when we're really far away from the right answer, kind of closer to the answer. And these here are going to be responsible for fine-tuning the answer. Okay, so now that we've written our inference program in our model, let's see the sorts of modifications that we can do. So because this is a probabilistic programming language, incrementally modifying the model should be relatively straightforward. So if we want to add a ceiling, right, all we have to do is just add a few lines of code, introduce a new random variable for the height of the room, right, because we don't know that a priori. And now our rendered images might look something like this on the left. But in order to do that, we need to adjust our inference program in turn, right? So now we need to somehow handle inference over this new random variable we've introduced. And we're just going to add another individual coordinate-wise move on that random variable, as well as add it to the block of updates we're doing on all the other ones. So now when we run inference, again, our virtual worlds have floors and ceilings. And I'll let it restart one more time. Right. Okay, so now let's see what happens when we adjust the model, adjust the inference program.
So you mentioned about the neural nets, so this big jump is the part done by the neural net.
So this example is not using the neural net stuff. Yeah, this is just basically proposing jointly from the prior again. So if you're in a really bad initialization, you propose, 10, 50 times eventually you'll move somewhere close. Okay, so let's see what happens when we modify this inference program. So say we wanted to do inference on a video stream instead of single images. Well, in Gen, we can do that pretty easily just by changing this for loop into a while loop and introducing an update to the data. So here we're basically taking a new frame from the depth camera every iteration, and we're forcing the trace to take that new value for observations. So this sort of, because we let users write their inference programs in regular Julia code, this sort of modification is pretty straightforward. Whereas if you did this in an inference engine, we'd actually have to modify the inference engine in order to make this change. Okay, now here are traces of MCMC plots for this particular inference program. And if I maybe change this inference program in different ways, maybe I delete this line, then I'll get some results where the convergence doesn't work quite as well. If I delete these other lines, I get some results where inference is bad in some other way. So the point of this is that basically the details of this algorithm matter, and you want users to have control over those details. And then another aspect of control, which is going to be really important for perception problems, is actually allowing users to use domain-specific heuristics to help solve their problem. So if all users could do was use things like MCMC with generic proposals or HMC, things like that, that's vastly limiting the set of algorithms they can apply, because there's all this work in computer vision on solving these problems, not from a probabilistic perspective at all, but we want to be able to use that work for our Bayesian inference problem. So I'll just give an example. Suppose we have this image here. We knew that if we could find 3 pixels on that floor plane, then we could just geometrically compute the right floor plane by putting the plane through those pixels, and then compute the relative angles analytically in one step. So maybe we can define a heuristic based on that. So what we do is basically and you can implement this in Gen, you randomly pick 3 pixels on the image, you fit the floor plane, and then you offer that as a proposal. And if you look on the left, the default proposal again is just the prior, so everything's uniform. On the right, with our data-driven proposal now, which is using this heuristic, sometimes we're getting sort of basically random planes because not all the pixels are going to align on those on the floor. But actually, with appreciable probability, we'll get pixels that do line up correctly with the floor, and that'll help us concentrate some of the probability mass around the right answer, which can make it more efficient. So this is the general picture of how efficiency works with these data-driven proposals. Basically, with a generic proposal, as you do more computation, you converge to the right answer, let's say in 0.51 seconds in this case. And with the data-driven proposal, you start off actually with more concentrated probability around the right answer, and you still converge to the right answer, but you just do it from a better starting point, so it takes less time. Okay, so that was our intro to what code looks like in Gen, and I hope that gives you some sense of how Gen's inference programming framework, where inference programs are just regular Julia code, is maybe a little more suited to sort of machine perception problems, where you need people you want to be able to use their existing heuristics and tweak the algorithm. So I'm not going to go into the system architecture, actually, but one of the key ideas there was around allowing users to incrementally optimize the performance. And so Gen uses a black box abstraction for modeling, and users can implement their own versions of that abstraction, or their own versions of that interface, if they want to incrementally optimize a piece of the system. But I don't think I have time to go into that. So Gen research directions that we're interested in are looking at specialized modeling languages. So basically, Gen is composed, because of this black box abstraction, it's actually composed of a set of different modeling languages. And users combine these modeling languages in different ways depending on the application. So extending Gen with different modeling languages is an interesting area. Also thinking of the interesting programming languages as the inference program itself, as opposed to the model program, which is what's most been standardly looked at in this area, is really interesting. So for example, what would it mean to synthesize inference programs, right? Basically automatically write those inference scripts. And again, there's also a lot of domain-specific work that we're trying to build on top of Gen. So there's been some work by a collaborator in the lab on a system called pclean, which provides a higher level modeling language specialized for modeling tabular data. Because as you saw, Gen has pretty low level abstractions, right? Just random variables, generic arbitrary code you can write. But pclean is more specialized. And also we're working on a domain-specific modeling language for machine perception. Okay, so that was the first part of the talk about Gen. And the second part will be about this other work called AIDE. And in AIDE, our first question is, what is the error metric we should use to measure the accuracy of an inference program? So we want error metrics that are going to be taking uncertainty into account, right? So is the algorithm giving us an accurate uncertainty quantification or not? So again, for this example, right, this is an example. Both of these have multimodal posterior distributions. So whatever error metric we choose, it should actually make sure that you caught both of these modes in your approximating distribution. So there's various metrics for comparing two distributions. We saw lots of discussion of KL divergence earlier. So KL divergence is this asymmetric quantity where you can either have KL from Q to P or P to Q. So here P is the posterior, so the ideal answer to this inference problem, and Q is going to be our inference program's output distribution. So if we choose one direction of KL divergence where Q is on the left, then this metric basically would rather have Q explain one mode and not both. But if we chose this other metric where Q is on the right, then we'd actually rather have Q cover both modes, even if it seems less precise and sort of gives a little bit too much uncertainty over the problem. So thinking about which of these metrics you want to use for problems like machine perception and robotics applications, well, the first one seems a little overconfident, right? It's completely discounting the existence of these other possibilities. So if it's doing some planning algorithm or choosing some actions, you don't want to just be ignoring those possible states of the world. And the choice here where P is on the left is underconfidence, or sort of has too much uncertainty. It says, I don't really know. So with AIDE, basically we wanted to use a metric which has this property where we actually want to make sure that we're ensuring that the algorithm covers all the possibilities. So we're going to try to include this P to Q KL divergence in our metric. Okay, so we're going to be trying to estimate the KL divergence. So here's what we're trying to estimate. P is the posterior on the left. So X is basically all the latent variables. Y is the data that we're given. And P is the posterior. Q is our approximating distribution. And this is the KL divergence when the latent variable is discrete. So first thing to note is that this is a sum or a high-dimensional integral, but in general, this is difficult to compute tractably in general. So instead, we're going to use a Monte Carlo approximation. And the standard simple Monte Carlo estimator for this involves sampling from the posterior a bunch of times, n times, and computing this log ratio of the weights. However, this seems problematic. So first of all, this means you need posterior samples in order to evaluate any algorithm. That doesn't make that much sense because, again, if you believe that this intractable sum is, if you believe that the sum is intractable, right, then you may also believe that sampling the posterior exactly is intractable. And also, this expression involves computing these probabilities, which on the top is the posterior probability itself, which again is going to be hard to compute exactly. And at the bottom, it's the probability that your algorithm Q produced a given output X. So I'll talk about how we resolve that second issue later. But the idea is that basically Q is a piece of code, right? So what does it mean? The code might not report its probability of returning a given value. It might just be able to give you values. Okay, so the way we're going to address this first problem of, well, I can't do posterior sampling, is we're going to say, well, okay, you can't compare against the posterior, but instead compare against some expensive gold standard sampler that you have. And this maybe doesn't make that much sense in the statistics application, where if you can do, if you have a gold standard sampler, you should just use that sampler. Why would you even care about, right? Why would you even care about the faster or worse one? But in a machine perception problem, it does actually make sense to compare a faster algorithm that you're going to use in your application, called Q, against a more expensive algorithm, Q gold standard. Okay, so now we've resolved one of those problems where we can actually sample from this gold standard program now. But we have these two other issues. So basically, this issue is that these are programs, they produce output, but they don't report the densities or the probabilities that they would produce a given output. So to do that, we're going to introduce a concept called meta-inference, which in some sense is has deep parallels to auxiliary variable techniques in computational statistics, but has an interesting conceptual interpretation in terms of meta-inference. So let's see what I mean by that. Basically, these probabilities here, Q, GS, and Q, are really marginal probabilities, where to compute them, you would need to sum over all the internal random choices made by those sampling algorithms. And those are denoted U. So this is another high-dimensional sum, and this, again, will be hard to compute in general. Exactly. So here's an example. If we ran a particle filtering algorithm, we would, I don't know how many of you are familiar with particle filtering, but basically we're sampling a number of random variables. Each red line or letter here denotes a random variable. So we're going through many iterations of the algorithm and sampling various random variables. We're choosing to fork certain particles, and eventually we get some output, and that's going to be what X was. So suppose you wanted to do inference in this model, right? So now I'm treating the inference algorithm as a generative model, and this is where the meta-inference idea is coming in. So the idea here is now I'm observing some random variable, the output, X, and I'm asking you, well, what is the execution trace or the history of all the random variables that happened inside this model that explain that X? And you can construct various ways of doing this, right? Various inference algorithms for this model. But one algorithm in particular involves generating a sequence going back through the state space and then running the algorithm forward conditioned on that sequence. And that's actually, that's known as the conditional SMC algorithm from SMC literature. Okay, so now we're going to modify our estimator, and that new estimator is shown on the left. And what we're going to be doing is we're basically running our gold standard as before, but then we take the output, X, from the gold standard algorithm, and we run our meta-inference algorithm on the algorithm we're trying to evaluate. And that I'm denoting by R. So we're basically sampling an execution history of that algorithm from R. And you can show that if you do it in this way, basically you can be estimating an upper bound in expectation on the scale divergence that you originally wanted. So anyway, and the details of this are in this NeurIPS paper from 2017. So briefly, basically to give an example, I know I'm a little out of time. Basically, if we had an HMM, and we were trying to evaluate how well we're doing posterior inference in this HMM. Well, here on the lower left are the posterior marginal distributions for some data set, right? And basically, so over time, there's a number of states, and over time, this is showing the probability that you're in a given state at a given time. So this is the right answer on the lower left. If we use sequential Monte Carlo algorithms with different amounts of computation as our inference algorithm we're evaluating, we get algorithms that are less accurate with less computation, shown in A. And as we increase the amount of computation, they sort of convert to the right answer. So how can we quantify that? Well, one thing you might ask is, can't you just take the difference of these two images, right? Like, I can just say, well, this has 0 difference from that image, that must be very accurate. Well, one reason why we don't want to do that is because this is a marginal of the true posterior distribution, right? So our distribution is a posterior on all these trajectories, and that's a very large state space. There's T, S to the T of those, where S is the number of states, right? So this would only be getting at sort of only be measuring a very limited summary of what's actually happening in the full algorithm. And the idea here is that, well, if you use a gold standard SMC algorithm as a to benchmark the less accurate ones, you actually get results which look identical to if you had used the posterior, which shouldn't be that surprising, right? If our gold standard actually has converged the posterior, then we should be getting the same results as if we were comparing against the posterior. All right, and just to wrap up with this AIDE section, basically this idea of meta-inference is suggestive that, well, inference algorithms are just randomized algorithms. They make random choices, so you should be able to implement them in probabilistic programming languages too, right? And treat them as generative models. And there's some ongoing work in the group on a system called MetaGen, which basically treats inference algorithms as just any other program in your probabilistic programming language. So both models and inference algorithms are implemented in the same language. And we're working, Alex Lev is the primary person working on this right now. But we're working on using that probabilistic programming framework to help automate this idea of meta-inference that I introduced earlier. All right, thanks.
Questions?
Hey, Marco, perhaps I missed during your talk is, in the first for Gen, you get 100 times speed up, right? What was the core reason? I couldn't understand that.
Yeah, so I didn't really go into the architectural differences between Gen and Venture, but one big reason was that Venture is maintaining this dynamic dependency graph among every single expression that gets evaluated in the program. That's a very heavyweight data structure, whereas Gen is using more coarser-grained tracking of dependencies. So not every little expression gets a node in that graph.
So as one possible future direction, you mentioned the verification of the user-defined inference algorithms. So what would you even want to prove about them?
So the second section on this AIDE estimator was basically about, I don't know if this is sort of basically was asking, well, how do we measure the accuracy, right? So that's in some sense verification, but it's really more of like a, basically it wouldn't be a formal proof, first of all, right? It's going to be an estimate of some divergence. And the idea is, well, I want to know if I apply this much computation, what's my error going to be? And maybe it makes more sense to apply this other optimization instead and get a less error, right? So basically being able to plot the time accuracy trade-off of these algorithms would be a useful thing for like perception.
So it would be probably something that's very specific to the domain, what you want to like verify about the... the thing that you implement?
Yeah, so that's a good question. I think what we're trying to do here is come up with a pretty, like a sort of a robust domain general approach based on KL divergence that's sort of covering the full posterior distribution, right? Because I could come up with any sort of projection of the distribution, like any sort of witness or any little function like the mean or something, and just compare those, right? But here we're aiming to get a more general one. Yeah.
Hi. So can you apply AIDE to compare, say, continuous and discrete distribution or hybrid distributions, or is it only for continuous ones?
So I haven't looked into this hybrid stuff. Yeah, I assume that would not be trivial. Yeah, but also like, yeah, I think just handling discrete distributions is definitely, basically when the supports of the two distributions match, this is something where KL divergence can be defined at least, right?
That's right.
So, yeah.
I mean, KL divergence is also has problems with this kind of mixes. I'm just curious.
Yeah, interesting. Yeah, I haven't looked into that.
Okay.
So one quick question on like the first half, these data proposals, like the data-driven, this is, where did they come from, these ones? Because you had in the example, they were not there, I guess, right? It was in the worked example, I think.
Yeah.
But you don't have to scroll back. Oh, you can.
Okay. So that was it's about the plane one, where I find 3 pixels in the plane?
Exactly. Like, yeah, this was the ceiling and the free coordinates, I think.
Right.
Yeah.
So
the data-driven proposal comes from where?
So it basically takes the image. It has some random variables, which involve sampling 3 random pixels, and then fitting a plane, and then returning that, and basically back solving to find what the angle of the camera is relative to that plane, which gives you an assignment to some of the latent variables of your model, and then it basically proposes those as the values. So that's like a data-driven proposal. Yeah.
Okay. If no more questions, let's thank Marco again.